My name's Anton Lord. I've worked in both industry and academia in a machine learning context. PhD was in health informatics, using machine learning to predict different kinds of diseases, everything from bipolar, major depression, anorexia, from the mental health side of things. I did some work in the gut health space, the colorectal cancer area, and a little bit in infectious diseases as well, things like malaria and dengue and that kind of stuff as well. I've spent probably 5 years as a postdoc, and then transitioned across to industry after that, where I work at Leapin as their lead data scientist. I introduced machine learning to Leapin, and whole machine learning operations systems is what I've set up there, alongside the other data science components. So today I'm going to focus on the machine learning operations side of things. So not so much about the specific problem cases, the specific algorithms which we've used, or the how we've gone about solving those, but more about how do we take a machine learning model which we generate, and how can we then make that usable in a production setting. So today I'll go through a little bit about machine learning in industry and what the growth is like, and comparing that against some of the other sectors. And I'll talk about the tech debt of machine learning. This is really where a lot of a disconnection comes between academia and industry. Where can you take something which you can develop as a proof of concept and bring it to life in a production setting? That is predominantly using what we call MLOps, machine learning operations. And so I'll go through what this is, how it works, what's so special about it, and why do we use it. I'll go for a little bit about how can you secure data, sensitive data, because a lot of machine learning is very sensitive to noise in your data. And so if you sanitize your data, you may not actually end up with an algorithm which suits the purposes as well as you would like. So I'll go through how can you secure PII and still allow your algorithms to use that in at least the training phase. And I'll go through how do we go about versioning and operationalization, of how can we then bring them into a production setting. And I will wrap it up with an example that we use in-house, but more just to touch on that whole process. So the machine learning sector has seen a massive growth in recent years. Estimates of the market size vary quite wildly, but market sizes in excess of 320 billion by 2030 are quite common in all the estimates that I've seen. And this is looking at a growth, or how they measure growth in industry, of about 33% year on year. So just to compare that to other sectors, a CAGR, which is the annual growth of above 8% for a company, is seen as good. CAGR in this, what I'm showing here on the right-hand side, is retail industry, and the average there is 5.7%. So when you look at machine learning and you say there's a 33% growth year on year, it's showing that we have a huge amount of growth potential, a massive amount of growth which is occurring, and at a rate which is not seen in other industries. So one of the problems which we need to deal with in machine learning there is trying to scale things up appropriately. How can you bring them into a way which you're not just looking at these smaller incremental gains, but you can find quite substantial teething issues if you don't plan for scale. So a white paper which came out a while ago, which is, I'm hoping many people here have seen, is called A Hidden Technical Debt of Machine Learning, and it's by Google. It was released by Google. And the main take-home message from this is, while we spend so much time and effort thinking about the machine learning side of things and building the machine learning code and refining the models, there's a lot of other components which are required to take a proof of concept machine learning model, or something which we can see in a closed environment that works, take that and bring that into a live environment. So there's a lot of things like feature extraction, data collection, data verification, which have to happen in a pipeline and have to be all robust. While if you're working in a if you're working with a closed data set, you have the time to make sure that you can prepare the data in an appropriate way and make sure that it's all cleaned appropriately and everything looks good before you start the process. When you're looking at a live environment, you need to be concerned with the edge cases of what could be coming in, what could be intentionally or unintentionally not fitting how you've structured it. So people can, like traditionally people would try and do SQL attacks on websites, for instance, when you're trying to access if you had a portal to a database. And so there are ways that people would try and intentionally alter the input to achieve something which you're not expecting. And then there's other things where you might just accidentally find data coming in which is in a wrong format or does not fit the mold, and so does not adhere the way that you expect it to. One example that we've got of this at Leapin is where people will submit us invoices, and some of these are quite large. You might find an invoice which is 10 or 15 pages long because they've just aggregated everything over a 3-month period. And if I've put this together as an extremely high resolution image, one of the internal systems might believe that this is a denial of service attack because of the amount of data it's trying to process, and so it can reject that particular invoice from the workflow. So it's all these kind of edge cases which you need to be concerned with the data verification, feature extraction side of things. On top of that, you need to worry about how do you serve the machine learning models, how do you make them available, and how do you monitor them after the fact? So how can we make sure that they're doing what they're meant to be doing and not doing not providing incorrect results or not providing results which have are inaccurate because of some kind of drift in the data or in the environment. So to do this, one of the things which has been brought in is machine learning operations. And this is really trying to bring together machine learning ops environments like a DevOps style. And then by bringing those together, you can start to bring in the rigidness of a DevOps environment with the machine learning side of things. And that gives you a lot more controllability over what you're seeing in a live scenario. So while you've got, in a best case scenario, you've got machine learning engineers in an industry or in a business which are developing the models which are being used and showing that these have business value, and on top of that, you've got MLOps occurring behind the scenes, trying to bring that together into a way which is able to be served to the front end. So people can access it either internal within the company or external if it's externally facing service. But the MLOps is there to allow you to have the robustness in the system and make sure that you have the availability of a system, and that you have consistent and expected behavior. So MLOps comes, it can be broken down into a couple of major components. And the first one is building our models. So this is going through the data collection and processing, feature engineering, building the models and validating and testing the models. So this is really what you would normally go through if you're working in a closed environment, where you would go through a single data extract, and then you'd go through feature engineering, building your models, validating those models and testing those models within the data which you had, hopefully appropriately sampling your training, testing, validation splits so you get the most accurate version of the world that you can. So that's one of the components which comes into the MLOps framework. You also need to have control structures, so you need to be able to version your algorithms. And I'm not just talking about a machine learning algorithm itself. I'm not just talking about a particular model and being able to say, I want to roll back to the last version of this model, which we approved for release. it's the entire system which you need to be able to version. So everything which allows it to generate and return the response which is required. If that's not only the machine learning model, that's it will likely sit inside some kind of container, and then you'll have a particular agreed upon input to that container. You might have some post-processing within the container before it returns the result. In an example like ChatGPT, they'll run through the large language model, which will then generate all these different outputs, which it could present back to you. They then have some control structures to say that there are certain types of responses which it should not be providing back to you, regardless of if it was generated or not. So, and these are safeguards to make sure that people don't ask for information about things which are illegal, or trying to ask for information which is sensitive about the system itself. So they've brought in some control mechanisms after the machine learning model, but before the response is returned to you. And all that needs to be somehow versioned as well, so that you have complete control. You can always roll back to a previous version to say that we have an expected input and output of that version, and the next version we have an expected input and output of the next version, which will be released. This allows for auditability. It means that you can identify what happened for a particular model and why a particular outcome was given. So if there is ever a reason why you need to go back and audit what happened in a particular scenario, if you have that level of versioning available, you can actually have something which should be a known input versus output, and you should get the same result every time. If you don't, there could be some kind of stochastic process in there, but hopefully that's not impacting it too much. Otherwise, you wouldn't have confidence in the models which you've deployed. Monitoring is extremely important, and we need to make sure that we not only monitor the expected outcomes of deploying new versions of algorithms, but we also need to monitor what's happening live in production. So you want to make sure that you're monitoring, firstly, pre-deployment. You need to say, what kind of impact is this going to have? And can we have an estimate of the gains and the losses of deploying this new model? And then once that has been agreed upon to say that those gains and losses, that particular model is beneficial to the point where we should be deploying it, we need to be able to monitor it in production. Firstly, we should be seeing, after it goes to production, we should be seeing those gains, and we should have a way to objectively measure those. It changes area to area or a problem to problem, how you might measure that in production, but it is essential that you look at what's actually happening throughout the overall process, and that the gains of the model are actually being realized to the entire process and to the end-to-end process, and not just gains in your optimization metrics. This monitoring can also, it's not only useful for creating confidence in what has been deployed, but also allowing us to create feedback loops. So this is where we can retrain the models at using different triggers. And you can do it continuously, where you say, I'm going to retrain once a week or once a month or whatever it is, once you decide on your cadence. Or you can say, once we find that the monitoring is showing that there's been some kind of degradation, that's the time when we should go through and retrain the model. So it can be useful for that as well. And it's a really good way to try and optimize between the cost of retraining and the instability of retraining versus the benefits of making sure that your models are operating in an optimal fashion. And like I said, we should be measuring return on investment. We should be finding some way that we can measure the business outcome for this. And so that all kind of falls into the MLOps monitoring side of things as well. In the deployment and integration, this is one of the big things that that not using an MLOps system you kind of lack. When you deploy and you're not using an MLOps system, you're basing it on someone creating a model and then embedding that model into the deployment in some way. but what happens is if something goes wrong with it, if you need to roll back to a previous version, if you need to try and replicate that particular model for any reason, it becomes a lot harder unless you have that versioning and integration into deployment platforms there. So you really should have a system where you have all the models in a repository, and you have all the code in a code base, and then you can deploy to any of the different environments. So typically a business will have a development environment, user acceptance testing environment, and a production environment at the minimum. And then you should be able to deploy to all of those in an automated way so that you can go through those different layers of testing before it actually goes out to impacting business outcomes. So how does it differ from the standard DevOps? DevOps has been around for a long time, and it's well developed, and it's very, very robust, the concept, and it's available on all the major platforms, all the major online service providers. So there are some things which DevOps and MLOps have in common, and there are some which are specific to MLOps. So things like having a consistent environment, having consistent code versions integrated into the CI/CD, continuous integration, continuous delivery pipelines, and monitoring of those systems to make sure that they are live to the levels which are agreed upon. That's all falls into DevOps, but MLOps is actually leveraging that as well to give the robustness to the machine learning, which was previously missing. On top of that, the MLOps expands on this so that we can control things like the data sets which are being used. We can have model versioning available. We can have the hyperparameters. The different weights can be stored within the repository, so we can switch between them, or we can deploy between them as needed. We've got metrics embedded in there, so we can have like with like comparisons in an automated or semi-automated way. And we can have workflows to go through the training all the way through to deployment side. So that whole training workflow to say we just want to trigger a retrain on new data, that kind of workflow should be inside here as well. The idea is the more which you have, which is consistent in the process, the less likely it is that someone has manually had to massage it through the process, and the more consistent and faster and it will be to go through the deployments. So the reasons why we want to use MLOps, we want controllability. We want to have the codes, the models, and the systems all need to be controlled in a way that we can tell what's going to happen when we deploy a particular version number of a system. Model versioning, so that we can compare and contrast between experiments, so that you can run like different data sets, or you can update how you're fine-tuning your models, or you can update the models completely to completely different models or a different solution to the same endpoint. We should be able to compare and contrast these in a single environment. We should be able to track the performance gains over time for the models. And this is both tracking training processes, but it's also tracking in production as well. We really want to be measuring data drift. So just because one of the things that I've had to explain to quite a few people in the DevOps space is that, or in the IT, but without machine learning background, is while there are many systems in IT that once you develop it and you deploy it, unless you change something with that system, it should be very consistent. You shouldn't see any changes in behavior. If you think about data ingestion forms, so you go to a website, you enter some data, and it pushes this through to a database on the back end. Once that's been created, if you lock the versions of everything, if you lock the system, the models, the system and the code that's used for that, it shouldn't change. You should see the same thing every time. With machine learning models, as the environment changes, and I'm talking about the broader environment, how people are behaving, for instance, as that changes, you'll see the models will be based on older and potentially incorrect assumptions. So you might find that recommendations are no longer valid. If you think about the ChatGPT space, specifically with the NDIS, National Disability Insurance Scheme, ChatGPT is version locked to a certain time. I believe it's up to 2021 now, when the data was curated for, which was used to generate the model. If you ask it questions which pertain to things which have happened since then you won't get an accurate answer because the world has changed. And so this is what we would call drift. So because people are expecting one outcome based on changes, based on a world that they know, but the model didn't know the same world, you actually see a drift. In the NDIS space, you find that there are changes to the rules quite regularly, changes to what's allowed and what's not allowed, how much people can charge for different activities. So if you were to use an NLP system for NDIS problems, and someone was to ask it, am I allowed to buy an iPad to assist with this? Then you might find that it gives incorrect information, because it could be that the government has changed those rules since the model has been trained. So we need to monitor drift in the data to make sure that it's still behaving the way that it's meant to behave. And then we should be triggering some kind of rebuild or some kind of retrain at a minimum to make sure that it's performing as best as it can be when the quality drops to a point where it's now becoming unacceptable. Something else which we can look at is inference monitoring, where we look for particular outcomes. We give it particular inputs and we look for particular outcomes. And if we don't get those outcomes, we can mark it as a failure. So with that, we can actually try and spike the data, spike the input to make sure that it's still behaving the way that it's meant to be behaving. So the benefits, some of the major benefits of MLOps is risk minimization. Let's start. Integration with existing ops systems. So if you use an MLOps system and you have models which are available, you can identify them through hash keys which are related to some kind of data store. It means that it's easy to integrate them into existing CI/CD pipelines, where you can state what version of a machine learning model should be used in a particular deployment just by changing the hash key in a variable. So you could set this up as a parameter which can be changed at deployment. You can have this as a runtime thing if you want to be able to switch live between them. But being able to integrate it with existing ops systems is one of those big things. Risk minimization, this comes down to having consistency, having understandability of what's happening, having controllability over the environment and the inputs versus outputs. So by providing that framework where you can be sure that you're using the same version of Python with the same operating system, all inside a particular container or inside a Docker, for instance, and this is deployed in a certain way, and having that consistency helps you to minimize the risks. And then coupling that with your ability to monitor what is meant to be happening in a production environment helps to gain confidence that this model will be performing this as well as the current model which is deployed. Scalability is also very important. And by having this set up so it can integrate with existing DevOps systems, it enables you to use the scalability that they have. If you use, as part of your MLOps containers, like a Docker or something like that, then it allows you to scale well, because each one of those is an independent unit and they can be connected, they can be scaled horizontally very easily if you have some kind of control mechanism above them, which can specify which particular worker runs the algorithm at a particular time. So in that case, you can gain a lot about scalability. So defining the stack which we use in machine learning or in data science to produce the models is quite important. And one of the blessings and the curses that you have in data science is there is a whole myriad of tools which you can use. So these are all different tools for different purposes, which can be used for different aspects and make your life easier as a data scientist, which means there's pretty much a tool built for almost any different problem or any different pain point that you're trying to resolve. The problem with that is, with that level of flexibility, we also have a large amount of variability. And when you're looking for controllability and consistency and integration with existing systems, that flexibility comes as a bit of a curse, because if you're trying to deploy a system and it's using an incompatible version with what's already deployed in that environment, then you're going to have problems. So restricting this down to something which integrates with the other systems and plays nicely so that you can have a consistent environment, that's really important. And for that, I would recommend using a template or something that looks like this to go through and define how do you want your stack to look. Make sure that it fits with the systems which are in the environment which you're trying to develop for. So once you go through and fill in one of these templates, and I'm happy to provide the link to this later if anyone wants it or needs it, you can end up with something that looks like this. And you just say, I'm using this particular environment. I'm using Python for my data analysis. I want to use Git for my source control, DVC which is data version control for some of the deployment, and the ML meta store. So where do I store the information? And registry, sorry, as well. And then making sure that your CI/CD process, your build pipeline, matches up with the existing build pipelines to try and minimize any inconsistencies you can have. So I've talked a little bit, I just briefly touched on DVC there, data version control. That is it's a particularly nice framework which allows us to store large amounts of data in a way which is secure. So if you have things versioned with Git for all your source code, anyone who has access to that source code has access to that Git repository, has access to everything in there. And this means that if you have things like usernames and passwords, as good practice, should never be inside Git repositories. You should have them in some kind of environment file which is not tracked, or as an environment variable which gets pulled at build time. If you had the data which you're using to train your algorithm inside your Git repository, then whoever could download that repository would be able to download all of your data as well. And if that had people's names, addresses, phone numbers, what services that they had contracted previously, next of kin, bank details, whatever it is that you've put in there to try and train this, they would have access to all of that. And that then breaks a lot of, well, it's incredibly bad for your data security. It means that every single person needs to be completely trusted with that. So instead, what we use is data version control. So when you create a Git repository, you can also install DVC in the same repository. And that means that you can have files which are not tracked in the Git repository, but instead it creates this .dvc file. So here you'll see down the bottom, you'll see this model.pickle.dvc. And that there is just a file that contains the hash for the location of the actual file. So where you would normally do git pull, git push to get your data or to push your data back, you can also do DVC pull and DVC push to pull the data from its own repository, from its own S3 bucket if you're using AWS. And this allows you to have different user credentials to access both. So someone can have access to the code repository, but not the data repository, for instance. And so that gives you that tighter level of control that you can then say that someone can have access to go through the deployment side, but not have access to pull all of the data and get all of the personally identifiable information. So MLflow is my tool of choice and the tool of choice for many for tracking experiments. I forgot this had an animation on it. Sorry for the zooming on this one. So what it does is it takes it takes your experiments. When you're running your experiment through Python, you then submit those results to MLflow. Your parameters, your metrics, your artifacts are all stored there. So you can track your artifacts. You can download them at build time if you're going for a deployment. You can then track how well the metrics of the internal metrics are measuring for the particular build, and it's storing it in a consistent space where it allows availability for both the build processes and for you to run locally. So how do we take your machine learning models and we put them into production? Well, the machine learning model itself needs to be served in some way. And for this, we typically use a Docker. It's a container, which is like a micro version of a virtual computer. So it creates just the environment with which is required to run the algorithm itself. It is probably the world standard, or the most used system in the world for this. So if you are looking to implement something which is readily updated and trusted, then Docker is actually a really good choice. You can take all of your machine learning code and all of the associated Python code, or whichever language it is, but all of the code around a machine learning model, and then you can place that into a Docker, which has an API. So you can submit a query into it, you push some data into it. It will then run through the process internally, running the machine learning model and any associated post-processing code, and then it'll return the result to you. And in this way, we can have some input data. We push it into the Docker as a RESTful API, and RESTful just means that it doesn't retain any information itself. It forgets as soon as it's given you the result. So we can put some data into it, and out the other end comes the predictions. And this allows us to integrate it with existing systems quite cleanly. So when you're deploying it in a cloud, you would have a system that looks like this. Flask, just so you're aware, is how we can connect a Python code to an API. So it's what allows the Python code to listen for a signal to come in. When the signal comes in, process the algorithm, or process the signal through that algorithm, and then send out the result. So we would have API access through some kind of security system. We would then go to a container which is running the Flask, and then that would be potentially communicating with a database on the back end. At Leapin, we predominantly use NoSQL or DynamoDB databases on the back end as our first data store. And then after the data becomes more structured, after we've gone through some other processing, we'll put it into a MySQL environment where it can be accessed easier. So model performance over time is one of the issues which I mentioned before. You can see when you train a model, you'll have a data set, you'll optimize the model for that particular data set, and you'll end up with hopefully something which has really good prediction accuracy, or at least good enough that it's value to be deploying this into production. After it hits production and the model doesn't change, but things about the environment changes, the types of queries which are coming in changes, the demographics of people submitting information changes, depending on what the data is about. So for instance, in that case, what I'm referring to is if we have people with different disabilities using Leapin, and if someone with a particular disability is asking for assistance, the type of assistance they may need could be quite different from someone with a different disability. Let's say someone who is paraplegic is asking for what services are available for them that can assist them to live their best life. Those services are going to be fundamentally different to someone who has severe and debilitating anxiety. So you might find that when you're if you're to develop a recommender system, those two groups would have very different needs. And so if you trained it on a user base which were predominantly physical disability based, and then you had more of an uptick in people with psychiatric disabilities instead, or psychiatric conditions. And this could be a change in government policy allowing or disallowing different groups from using the NDIS. Then the recommender system would be built on the wrong information. It would be built on a group which is no longer as relevant, and so the performance would degrade. So we need to monitor for this in production. And we need to perform retraining when this occurs. So the two major ways which we can perform retraining are either through periodic retraining, and this is where we have an acceptable cadence to retraining. We might say that we want to refresh the models once a week or once a month, just to make sure that we're using the latest data and that it's performing as best as it can. Or if you can get it to work a little bit smarter for you, you can use metric-based retraining. So you can monitor metrics in production, and you can say when these metrics start to dip, when we see changes in either what's coming out of a machine learning algorithm or what's coming out of a process, or changes in the statistics of what's going in. You can look at measuring drift in the input data, and as that drift changes, you could say we now want to do a preventative rechange or a proactive retrain to make sure that we are training it on data which is most like the data which we're seeing being submitted by users or into the system. So those are the two main ways which I would recommend doing retraining. Typically when setting up a system, I would normally go for setting up a periodic retraining to start with, and then trying to find what metrics are going to work for using that as a metric-based trigger instead. And that allows you to deploy the system sooner and get them into production in a way that you're seeing benefits, and then have an understanding about how that maps back to something which is more nuanced. So MLflow, as I mentioned, it is a way that we can track all of our different experiments. Here's one of the experiments which we use at Leapin. This one is for processing invoices. So it's actually a convolutional neural network, two-dimensional image processing, and we're looking to process invoices using a deep neural network. So we've trained a bunch of different models over the months to try and identify which one goes to production. What you can see here is all the different versions of the models, all the different train times, and in the middle you'll see that something called models, which is firstly, it states what it was built off. So these are all based on PyTorch, but then it gives it you'll see invoice interpreter 13, 14, 15, 16. This is where we have accepted these to go for deployment. And so we've registered those models as the next iteration in deployment. And that allows us to say, if something went wrong, we can roll back from version 16 to version 15. We have a very clear understanding about, firstly, what code was deployed alongside that and what model was deployed at the same time. On the right-hand side, you can see the different metrics which we've been tracking as a way of looking at the goodness of fit internally. These don't necessarily map up to the end result, because we have been changing both training, testing, and validation sets in this process. So as we've expanded our testing and validation sets, you can actually see degradation in these metrics where that is a better measure of reality than something which is more contrived on a smaller data set. So what I would recommend, instead of using just those internal metrics, even if it isn't a training, testing, validation split, is trying to find some way to measure the performance of the algorithm for what does it mean for the business. Typically, businesses don't care about the loss function or the accuracy of the training period. They care about why do we care is the question which they're going to ask. What business value does this give? And in this case, what we're looking at is, if I pushed 1,000 invoices through the system, what percentage of these invoices would I find different components on and report the correct values for those components? So in this case, I'm actually pushing through invoices where I know the gold standard, and I'm looking at what percentage of the time do I find the correct information from the algorithm. So that gives us our level of confidence and how much can the business gain from it. And here we're looking at two different runs. We can look at each metric in line and see, do we see a gain? So we can say invoice total hit, we went from 87% up to 90%. So that looks like a net gain. So that would be a reason why we might recommend to promote this to production. And that's what we use as our objective measures for how well will this particular update be received by business. Once it has gone to production, and I apologize for the lack of labels on this, but because it's sensitive information to the business, I felt it was best to remove the labels itself. We can look at operational efficiency. So what I was showing you before was what percentage of the time did we find different components on the invoice? And what I'm showing you here is how many invoices can we process per day per person. So this is essentially tracking, as we deploy different versions of the whole software system, how are those gains being received by the business through the entire process, right to the end of where people need to manually intervene, showing how that is all flowing through. So this is the actual business gain at the end. But why do we care? Is can we make it more efficient? Can we get more people process, or can we get people to process more invoices in the same amount of time with the same effort? So I'll give you a brief rundown of an example, but I'm just going to keep this very brief because I want to keep some time for questions at the end. So this is to do with Leapin. This is my primary business, or primarily workplace. I also do some consultancy on the side, but this is what I do most of the time. We work as a not-for-profit plan management company, which means essentially we are assisting people to pay their invoices for services that they need, which are approved by the NDIS. We're leading for inclusive employment movement, so we have an active, we actively try and look for people's abilities, not their disabilities, and try and hire people with disabilities into roles where they can function quite well within the company. We have over 11,000 members nationally, and we have over 50,000 service providers for those members. And for this, we have about 100 staff, a bit over, I think it's about 120 staff now. So the problem which I was trying to solve here is trying to keep invoice processing times down. We process over this is a bit old now, it's probably over 2 million claims per, it's easily over 2 million claims per date. We process, it would be over 35,000 claims per week now. And for this, we have a fixed amount per member, which we get, which I believe is about $110 now. So we need to try and keep this efficient, and this is where artificial intelligence can really come into its own. Originally, what they were doing was Leapin was doing this manually. They were getting invoices emailed into them. They had someone open up the invoice and write down all the details into a way which we could then submit it for payment. This is extremely time consuming, and a good day for someone was about 80 invoices, or even less. Nowadays, every day we have people doing over 300 invoices. It was a few days ago, we had 500 plus. The record is about 800 in one day. So we've designed a much more efficient system now. After complete manual processing, they went to a traditional OCR system, which was based on bounding boxes, where you said anything inside this area of this particular template belongs to this particular thing. The problem is when things move around, if someone adds or removes line items, then it can change the locations of things. And as soon as they fall out of a box, then it falls over and it doesn't work. So to solve this, we brought in a convolutional neural network. So this is where we can read the image in 2 dimensions. We can identify different objects, be it BSB, ABN, person's name, the provider's name, the dollar value, all of that information. We can find the patterns which match those, and then we can read those, pull it apart, and then process the invoice. So the algorithm we used was called YOLO version 5. This was originally set up to identify things like people, dogs, cats, tires, balls, those kind of image components, but we just repurposed it. Instead of looking for that, we ended up looking for pieces of an invoice. Could we identify an invoice total? Could we identify a BSB number, account number? NDIS number, date of birth, invoice number, all this kind of stuff. So we just repurposed the same algorithm for that. We track this experiment I showed you before. We actually track that through MLflow, and this gives us confidence about whether or not we actually go through and attempt doing an A/B test on this to say, is this actually working better as an end-to-end process? And then after that, we look at how can we give confidence for deploying this throughout the whole process. So MLflow, which is one of the components of MLOps, is our way of getting those initial signals to say, yes, this is improved, and tracking. That's one of the reasons we use it here. The other one is to allow us to roll back easily and to track what have we done historically and compare and contrast between them. Then we go to A/B testing, where we look at comparing against a gold standard and where we know the outcome of everything. And then from that, we look at, is this beneficial to what is currently deployed? So in this case, what we've got is on the left column, we have what is currently deployed, and at the time that I took the screenshot anyway, and on the right column, we have what is proposed for deployment. So the main take-home message here is the STP, which is the number of invoices which no one had to intervene for at all, that had every single data point captured exactly correctly and could be processed without human intervention. That is the primary measure for how successful we are. And then showing an increase in that, as well as the breakdown to show that it's an increase across the board for all the sub-measures, is our metric to allow the business to gain faith that this will work in production as a user acceptance testing without having someone go through and manually push through 1,000 invoices and check them, or spot check and hope that they got a lucky break in the data. And then after that, we perform live monitoring of this. So we look at week on week, what is the number of invoices which we're processing completely hands-free. We also look at track a whole bunch of other metrics as well, but this is that single metric which tells the business that we are continually improving the system. So while that doesn't elicit all the different components of MLOps, hopefully it's shown you how we use a couple of those, and that helps us to link back into the business to gain confidence in the business and provide a robust and always available system. I'd like to thank you all for listening, and would like to open the floor to questions.
Thank you, Anton. Very interesting stuff. As we said, we'd like to open it all to questions. So any questions from the audience? I see Ryan Covey and Claire both have questions. We'll go with Claire and then Ryan.
Thanks,
Claire.
Jerry. Normally I'd say I think Ryan got there first, but I have to go to another meeting in 5 minutes. So I might take the opportunity anyway. Thank you, Anton. It's been a very interesting talk. I was look at MLOps and think it feels like a lot, like when you're starting from having nothing and looking at all those different components of it. It feels like a lot, especially, yeah. Is it the kind of thing where you have to like take a big jump and just do all of it, or are there kind of like baby steps that you can take? Like if there are parts where you're like, I can't do all of these different bits, what might be the most important parts if you were just sort of going to work your way up towards the whole big picture of it?
Yes, absolutely. So there are things you can do as baby steps along the way, and it absolutely does. It is a lot in that whole process to get it set up. There are commercial solutions which can assist with that to smooth over that process. So things like Selden, for instance, have a really good system where they integrate a lot of this out of the box, but they do charge you for it. I believe their entry point is $70,000 US per year. So it's a high bar to use it. So I would say that if you already have models in production, if you're using artificial intelligence in a production setting, first thing I would try and bring in there is monitoring. Can you understand how you're mapping what you think is happening with models with the outcomes? Can you show that that is still consistent? So that's the first place I would look. And then I'll try and go back to integrating this into the robustness side of things. Because if you don't know what's happening, if you can't monitor how it's impacting what's happening on the other side, it's going to be really hard to find a trigger to go and say it's worth rolling back now. So I think that's more needed as you know what you know, as opposed to as you've got things set up. And like if you've set up, I can go forwards and backwards through my versions, but I don't understand when it's not working, then you're not going to go backwards in a version. So monitoring is the biggest one, which I'd set up first. After that, I would be linking into the CI/CD pipelines, and you can do that just by copying the models in there to start with. So you can actually have in a Git repository, you can store the model, assuming it's nothing sensitive in the model weights itself. And then after that, you can build in your ML flow so that you can then bring it in from its own personal model store. Having said that, from a governance perspective, making sure that your PII is protected absolutely should be first port of call. So never store your data in a way which it unintentionally gives access to anyone else. So that's really the way which I'd say you can deploy it. I appreciate you've got to run to a meeting, but if you want to connect, I'm happy to discuss further.
Okay, thank you.
I suppose I'll jump in. Hi, Anton. Thank you very much for a very interesting talk. I was interested to know, you mentioned that you have a process where you're, you've got a model that in production that attempts to read an invoice and extract all of the information that it requires for the NDIS claim, if I've got that understanding correctly, and then if all goes well, you can automatically process that invoice and then make the claim. If it doesn't go well, then you hand that off for manual intervention. And what I'm interested to know is, how do you catch the model before it's about to submit incorrect information, for example? So are there uncertainty measures that you use where you have maybe the model provides some form of confidence that, I'm very confident or I'm not so confident, and if there's a threshold that's breached, maybe you then, involve manual intervention, or perhaps there's some other way of doing it. But yeah, I'm interested to know how you catch the model beforehand, and whether you've had any kind of experiences with situations where maybe there's one that slipped through the cracks and you submitted an incorrect claim, and how that goes.
Yes.
Thanks.
Absolutely. So there's a couple of places where we put in cross checks and balances to make sure that the information which is accurate before it's submitted. Because this is financial information, I would put this as nearing the banking sector in terms of what kind of confidence you should have. So we need to be very certain that what we submit is actually real and is accurate before it goes out. Each of the different fields which we capture does have its own confidence score. So all of those fields need to be above the relevant confidence scores to make sure that we accept that it is ready to go for submission. We tailor those confidence scores based off the recent history. So we have a system set up to take the information which has been submitted recently, look at what are the confidence scores which were created and how many of those values, and were those values modified or not before submission. So with that, we can actually fine tune what confidence score for what metric is optimal. And we set the threshold for that very high. On top of that, we do external, externals and outside the model cross checks as well. So do we know a particular member by name and by NDIS number? If not, then that has to go for validation. Same thing with a business. Do we know the business by ABN, BSB and account number? Do they exist in our database and our internal database? If not, then it has to go for validation. Does the total dollar value match up with the sum total of all the line items? And the line items, does the units times the unit price match for line totals? All of these are cross-checked before it can go to submission. We also check NDA, the item codes, for instance, to make sure that all the item codes which were extracted are known by in the most recent price guide. So anything which doesn't fit certain schemes, we make sure that it gets suppressed. Anything which doesn't have complete data, then it goes to manual intervention. And when it goes to manual intervention, we pre-populate as much as we can as an efficiency gain. So let's say 90% of the details we're happy with, but there's a couple there which we're uncertain of what's going on. We'll pre-populate everything else, which can be modified by our team, but it at least saves them the effort when it's mostly correct. So some internal validations, which are to do with the confidence score, and then some cross checks to our database itself to make sure that it matches against what we know about that member and the behavior of that person.
Yeah, but that all sounds very thorough. Thank you very much for a great answer.
No problems. We have had one case where we had an incorrect hit that went out. And that was where someone had a double-barreled last name and the second part of a last name matched the full last name of someone else. And all other
details. Yeah, I see. Pretty unusual sort of case.
Yeah, very much an edge case, but I believe we've got less errors than we have in the manual processing.
Sure. Well, that's the benchmark, I suppose. If you can do better than the manual processing, you're already in front. So
yeah,
great.
Absolutely.
Thanks.
Yeah.
Great. Thank you, David.
Thanks very much, Anton, for a fascinating presentation. Thinking about the MLOps framework, does it have clear relationships to accountabilities? So like when a machine learning system is deployed, is it well understood who's answerable for it, or is that something that the framework doesn't really address?
So the framework itself doesn't assign who's responsible, who's liable when an algorithm is deployed for adverse outcomes. It's a question which I've seen come up legally, or some people questioning the legal implications of who is actually liable when it happens from time to time. It does give you more understanding about who was responsible for an adverse outcome. Because if you can track it to a particular model and you can track that model to who trained that model, you understand where that particular issue came in. And with the source code, with the post-processing, because that's all inside for us a Git repository, which is all like you can track to an individual who committed a line of code. So you can actually track it down to, here was an error which was brought into production. It had this adverse outcome. When we go back and look at who committed that error, this is a person who committed it. This is a person who approved it for release. So you do get that kind of auditability about it.
Right. Thanks.
Great, thank you. Very interesting. Okay, I guess we either got time for one more question, or we can wrap it up since we're over time and I'm certain other people have other meetings to get to. So any last questions for our guest Anton?
Ryan's got their hand
Ryan
up.
still has his hand up, so I don't know if he has another question or he... No question.
Sorry, I had just had that up from before and I never took it down, but I've taken it down now. Thanks.
No, that's fine. Okay, well, let's thank Anton for a really interesting talk. Lots of good points in there. Thank you very much indeed. And with that, I will conclude this meeting for the week. Thanks again.
All right. Thank you.